Hey, so in this video I will show you how to solve some optimization problems, right? Using derivatives. And in the second part of this video I will show you how to find differential and how to use differential to approximate the change in function. All right, so here's the first problem. We have some square piece of material, okay, and the side of this piece is s equal to 24. So since this is square, we have 24, 24, 24, 24. And then now we will cut off corners in here. So suppose the side of this is just x, right? So we cut 4 corners, right? Just 4 squares from 4 corners. And then we turn them up. Okay, we turn them up, we get a box. So the box looks like, you can imagine about it. The box looks like this. Some kind of, this is the box. Okay, so this is the box. And the box is open. Okay, the box is open. This is open box. So our problem is to find the maximum volume, right, among boxes. Okay, we need to find maximum volumes among boxes. So since they ask us to find maximum volume, first we need to find the volume function, right? We need to find the volume function. Once we have the volume function, we try to maximize, right? Try to maximize this function, or just find the maximum, or in this case, absolute maximums of this function. So let's say, what do we have, right? If you compare this picture and this picture, so basically we make a corner, right? So the height of this box should be x, right? The height of this box should be x. And of course the base of this box is also square, because we cut 4 corners in here, and 4 corners have the same side. So basically we need to find this side, right? This side, this side, this side. Okay, so what is this? This is s, right? Since we cut x in here, we cut x in here, h inches in here, so in total we have s equal to 24 inches. So that means the side of the base is just s minus 2x, right? The whole s subtract by this guy and this guy. So we have s minus 2x. So I can write from here s minus 2x. And now, we already have some volume function. So the volume function is equal to the base, the area of the base multiplied by the height, right? So the area of the base is s minus 2x squared, and then times x. So that is our volume function. Okay. Here, we still have a assumption. We have assumptions or not? Actually, we don't have. Oh, yes, this is the only one assumption we have, right? So the constraint in this problem is, since x is the distance, right? This is the side of each corner in here. So see, if you add 1x and x in here, so you have 2x. 2x is always less than or equal to x. So that is our constraint. X should be, of course, greater than or equal to 0, but less than or equal to s over 2, which is 12. Okay, let me tell you one more time, right? Why we have s over 2 in here? Because when you add x in here and this x together, so you get 2x, right? 2x should be less than or equal to s. So that's why we have x less than or equal to s over 2. And now, we have some polynomial in this case, right? And in order to find global maximum, we just need to take derivative to find all critical points. And then we compare function values at critical points and at 2 endpoints. So from there, we can get global maximum. Okay, let me erase this picture. Okay, erase this picture, and then let's say the function here is s is 24, so I can write 24. I write y equal to 24 minus 2x squared times x. Let's differentiate this function. So when you differentiate this function, you get y prime equal to. I can use the chain rule, no problem. So I bring the power down, and then I have 24 minus 2x, okay, and then multiply by the root of the inside, which is -2, and then times x, that is the root of the first part, and then plus the root of x is just 1, right? So I have 24 minus 2x squared. Okay. Now I don't distribute this because I see 24 minus 2x, 24 minus 2x. I need that. I just factor that out, right? I get 24 minus 2x. All right. Now inside. From this term, I get 2, 92, and x. 2, 92 is 94, 94x. So I have 94x. And then from here, I get plus 24 minus 2x. You see? So we already have a very beautiful form. And when you set this equal to 0, to find all critical points, you see 24 minus 2x equal to 0, or this part is equal to 0. From here, you can say that is 24 minus 2x equal to 0, or here's -4, right? -2, together I have -6. -6 plus 24. So I write -24 minus 6x equal to 0. From here, I can get x equal to 12, and from here, I guess x equal to 4. So our volume function has 2 critical points, right? And here's the endpoint. Now I just need to compare. Function values at 12. The function value at, okay, I write y 12, and then y at 4, and then y at 0. And as we can see from here, when you plug 12 into this function, you get 0. You plug 4 into this function, 0 into this function, you get 0. And when you plug 4 into this, you get 4 times in here. But that is 24, right? 24 here, I have 8. 24 minus 8 is 16. 16 squared, okay? You take 16 squared multiplied by 4. So you have 4 times 16 squared. You can use calculator to find that number, okay? So that is our answer. The maximum volume of this is 416 squared. All right, let's move to the next optimization problem. Simple. In this problem, we are given a parabola and a point, which is not on the graph of this parabola. And they ask us to find the closest to the given point. So the parabola is y equal to x squared minus 5, okay? And the point P is 0 to -4. So let's graph this parabola, and we'll see here we have x, o, y. So the vertex of this parabola is 0, right? 0 and 95. So I have 0 and 95 in here. This is the vertex. And at this point, the function attains global minimum. What is x intercepts? So you set this equal to 0, you get plus minus 5, right? Square root of 5. So I can write negative square root of 5, and here square root of 5. So you connect them. See? And we have parabola. So not very clear picture, but it's fine. That works. When x equal to 0 or y equal to -4. So here's -5, right? So -4 is around here. And this is our P. I'm writing here 0 and 94. Our problem is to find the closest point on the parabola to this point. So the closest point means we need to find the point. If you pick any point in here, right? For example, if this is the x, So you can calculate the distance between two guys. And the closest one, if this distance is minimum, right? Find the closest to the given point. So that means the distance is minimum, means we have to find the distance between 0, -4, and any point on the parabola. Okay, that is the first observation. So we are talking about distance, right? Because the closest means the minimum distance. Secondly, if you pick any point from the parabola, suppose that is x and y, right? So x and y should satisfy the equation of the parabola. That means this is the point x and then x squared minus 5. So this is the second observation, okay? So basically, we have to calculate the distance between this point and this point, okay? And we minimize that. So here's the distance. We have square root of x minus 0 squared plus y, in this case x squared, minus 5 minus 94 squared. Okay, so basically that is x square root x squared and then x squared minus 1 squared. Alright, so we have distance function, right, between the given point and arbitrary point in here. So again, if we need to find the closest one, we need to minimize this function. Alright, okay, let's minimize that, right? And we don't have any constraint in this case because, x, our points in here just moves along the parabola. So x can take negative and positive value. So that's fine, no constraint. But I don't like square root. I don't like square root at all because it's complicated to differentiate this function. So here's my observation. I say this distance is minimum if and only if the square of the distance is minimum. Alright? So I write this distance is minimum if and only if the square of the distance is minimum. So what is the square of distance? This is x squared plus x minus 1 squared. You see, we have a very simple function, right? So instead of considering the distance, I consider the square of the distance. Because I want to make that simpler, okay? This is very easy function. So we need to minimize this guy. Let's differentiate this, find all critical points, and make the chart for the first derivative. And we'll see where the function attains global minimum. So let's take derivative y prime equal to 2x plus 2 times x minus 1, right? And we set this equal to 0. So you have 2x, with the 2x I have 4x, and then 2 minus, with 91 is minus 2 equal to 0. From here I get x equal to 1 over 2. X equal to 1 over 2. But right now we don't know, right? Because this is just critical point. We don't know which is minimum, which is maximum. So we have two ways, in this case, two tests. Because we have the first derivative test and the second derivative test. This function is very easy. We can use the second derivative test. So if you differentiate one more time, so the second derivative is equal to 4. From here you get the second derivative equal to 4. 4 is bigger than 0, right? 4 is bigger than 0. That means our function, basically, that means our function, when the second derivative is positive, our function is convex. So convex looks like this. So in that case, the action point should be local, and not only local, but global minimum. Make sense? So since this guy is positive, I can do conclusion that this guy is minimum. That guy is minimum. So this obvious that the square of the distance is parabola, right? And the coefficient of x squared is positive, so that's why your parabola looks like this. Okay, so you have global minimum out there. And since they ask us to find the closest to the given point, that means we have to find x and y coordinate, right? X and y coordinates. So here we already have x coordinate. In order to find y coordinate, I just need to plug. I just need to plug x equal to 1/2. It looks very strange to me. Oh my goodness, I did a mistake, you see? I did a mistake in here. Here should be square. So it looks very strange to me. Let's fix that. Here I have x squared and here I have x squared. X squared out there. So I still have 2x in here. I have 2. Here I have x squared, right? But again, I need 2 times x, this guy, and then 2x. We use the chain rule. Fix that, please. Sorry for that. I have 0 in here. And in this step, okay, we did not finish this problem at all. So in this step, again, we factor 2x out, right? We have 2x out. From here I get 1. And from here I get plus 2x squared minus 1 equal to 0. You see? And here I have x equal to 0, right? And from here I get 1 plus 2x squared minus 2 equal to 0. So basically 1 with -2 is -1, and I bring into another side, I get 2x squared equal to 1, right? 2x squared equal to 1. So if we have 2x squared equal to 1, I have x squared equal to 1 over 2, and then x equal to plus minus square root of 1 over 2. You see? X equal to plus square root minus 1 over 2. And now we need to make the chart for the first derivative. There's no way to avoid that. So I have x, y prime, and y from negative infinity, negative square root of 1 over 2, and 0 in here, square root of 1 over 2, and then infinity. I get 0, 0, 0. You see? So the function, our square of the distance, has 3 critical points. So we have 4 intervals, right? We have from each interval we need to pick 1 point in order to consider the sign of the first derivative in here. So basically, I can write here's 2x squared minus 1. I can pick, which is very close to, or let's say from here I can pick 1, right? And from here I can pick -1. If I pick 1, I plug into this, I get positive. And here I get negative in here. So probably you have the following picture, right? So you can see the function is decreasing on this interval because the derivative is less than 0. In here the function is increasing, here the function is decreasing, and here the function is increasing. And here is your minimum. You don't care about the maximum because they ask you to find the closest point, right? We are minimizing the distance function. So basically, we might have maximum, absolute minimum at this point or at this point, right? Or maybe at 2 points, at problem. In our case, our distance square of the distance will attain global minimum at points. Why? Because we have square in here. See, we have square in here. So our function is symmetric, is even, right? So that means, whatever you had, you plug negative square root 1 over 2 or square root of 1 over 2 into this function, you get the same value function, the same function value. So basically, here is your answer, right? So basically, you have x equal to plus minus square root of 2. So you have 2 points out there, okay? The reason we have 2 points because our function, you see, at the beginning, the parabola looks like this. The parabola looks like this, and the points look like this. If you have 1 point from here, right, which is closest to this, so you should have another guy which is symmetric with respect to the y axis. So that's why we have two solutions in this case. All right, next. Next, we are talking about differential. Let's find differential of the following function. Find dy y equal to x square root of a minus x squared. So, what is differential? Differential is what? Just write right here, right? dy is equal to y prime dx. So basically, you need to find the derivative of the given function, and then you add dx at the end of that. So this is again differentiation rule, right? We have product. We need to use the product rule. So the product fg derivative is f derivative g plus fg derivative. In this case, f is x, g is the whole thing in here. So I have dy equal to, I write in here dx, okay? So we will not forget about that. Everything in here is the derivative of the function. So first, the derivative of f is 1, right? So I have square root of a minus x squared plus x, which is f. And g prime, so how to, in order to take this derivative of this function, we'll convert that into power function, because the square root is a minus x squared and then 2 1/2, right? 2 1/2. So I use the power rule and the chain rule for that. I bring the power down, that is 1 over 2. I reduce the power by 1, I get negative 1/2 in here. And here I just copy a minus x squared, right? And then I multiply by the derivative of the inside, which is negative 2x. So done. If I don't ask you to simplify, don't do that. Don't waste your time. All right. So the last question. Use differential to approximate delta y, I mean the change in the function. So in here, we can write, yeah, dy is approximately equal to delta f. What is delta f? Delta f is the change of function. If x changes from, x make a little change, so basically that is equal to f of x plus delta x minus f of x. When you add a little bit, right, to the variable, so your function also change. But sometimes it's complicated to calculate function values in here. So sometimes we use differential. We use differential to approximate that. Okay, so that's how we can use differential to do this. And our function looks like is the problem 4, right? We have y equal to 0.4, x cubed, x to 4, x equal to 1, delta x equal to dx equal to 0.1, and you need to find delta y and you need to find dy. So what is dy? I mean, this is delta y, right? Delta y or delta f. So in order to find delta y, we just plug numbers into this. So the point x equal to 1, delta x is 0.1, right? So basically I have 0.4 times 1 plus 0.1 to the 4 minus 1 or no 0.4 times 1 to the 4. Yeah, and you can use calculator to find this number. And if you use differential, that means we have to find the derivative of the function, right? We have to find the derivative of the function. So what is this? I write what derivative of this guy is equal to 0.4 times 4, and then x to the third, right? And I evaluate this when x equal to 1, right? And then I multiply by dx. dx is 0.1. You see? And of course, if you compare two expressions in here, you can see that, yeah, if we approximate delta y via or using differential, our computation would be nicer. simpler, much simpler. You see, here you plug 1 into this, you get 0.4 times 1 times 4 is 1.6, and then multiply by 0.1, you get 0.16, and that's your answer. And actually, this is approximately equal to this value. Okay, so I think that is the whole practice test on this Friday. So I hope that you enjoy this video, okay, and see you on Friday.